Here is a square wave. It sits flat, jumps straight up, sits flat again, all sharp corners and vertical cliffs. I am going to build this exact shape out of nothing but circles, smooth round things with no corners anywhere, which should sound impossible. Start with one arrow. It has a fixed length and it turns at a steady speed, one full turn per beat. Its tip does the only thing it can do, trace a circle. Now watch only the height of that tip, how far above or below the middle it sits, and plot it against time. As the arrow turns, that height rises and falls in a perfectly smooth sine wave. One circle gives you one sine wave. The arrow's speed is its frequency, how many turns per beat. A slow arrow draws a long, lazy wave. A fast arrow draws a tight, rapid one. Speed and length are the only two knobs we have. But a sine wave is round and gentle. It looks nothing like a square wave. One arrow will never give us flat tops and sharp corners, so we are going to need more arrows. So attach a second arrow to the tip of the first. It rides along, spinning on its own, and its height stacks on top of the first arrow's height. 2 arrows, tip to tail. Let me just try 3 times the speed and 1/3 of the length and see what happens. Watch the combined height. The pure sine starts to flatten at the top and steepen where it crosses the middle. It is already inching toward the square. Why 3 and not 2? Look at the square wave's own symmetry. Shift it by half a period and it flips upside down, landing exactly on its own negative. A sine only flips like that when its speed is an odd number. Speed 2 proves the point. Shift sine 2 by half a period and you get sine 2 straight back, not its negative. It has the wrong symmetry, so the square wave can contain no even speeds at all, only 1, 3, 5, 7 and onward. Good. The speeds are settled, 1, 3, 5, 7. The only thing left to pin down is how long each arrow should be, and guessing is not a plan. Here is the trick that makes the whole thing work. To find the arrow spinning at speed 3, spin the entire picture backwards at speed 3. The speed 3 arrow freezes in place and every other arrow keeps turning. Now take the average position over one full loop, the center of mass of the whole trail. Anything still spinning points every direction equally, so it averages out to 0. Only the frozen arrow is left standing. So unrotate at speed 3, then average, and what comes back is exactly the speed 3 arrow, both its length and the direction it started in. The curve hands you the circle that built it. For our height signal, that averaging becomes a clean recipe. Multiply the signal by the sine at speed n, average it over a full period, and read off the length of arrow n. Same move as unrotate and average, now with real numbers. One subtlety worth trusting. Measure sine against its own self this way and you get exactly 1. That calibration is why the recipe returns the true length of each arrow and not some scaled version of it. Run it for speed 1. Over the half period, the signal is just +1. The integral of the sine comes to 2, and the length lands on 4 over pi. That is the first arrow, no guessing. Speed 3 gives 4 over 3 pi. Speed 5 gives 4 over 5 pi. The lengths fall off as 1, a third, a fifth, a seventh. Read straight off the wave, exactly the shrinking arrows I sketched by hand earlier. And speed 2? The integral collapses to 0. The recipe itself throws out the even arrows, the exact symmetry we spotted earlier, now falling straight out of the arithmetic. The average also carries a direction, and that is the arrow's starting angle. For this wave, every arrow starts pointing the same way, which is exactly what a pure, balanced sine looks like. Slide the wave sideways in time, and all those starting angles swing around together, faster ones turning faster. Now stack them and watch. One arrow, a single round sine, nowhere near square. At arrow 3, the top flattens, the crossing steepens. The corner is starting to hint at itself. Arrows 5 and 7. Flatter plateaus, sharper rise, corners forming out of curves that individually have no corner at all. 20 arrows. 50. The round signs have fused into flat plateaus joined by near vertical walls. Roundness, added up in the right amounts, has become a corner. One honest catch, right at each jump, a little overshoot, sits there and refuses to leave. Add more arrows and it gets thinner but never shorter. The sum equals the square wave everywhere except exactly at the cliffs, where it lands right in the middle of the jump. Step back to the arrows themselves. Chain them tip to tail, let them spin, and the tip's height over time is the square wave. The same reading trick, unrotate and average, pulls every arrow out of any repeating signal you hand it, however jagged. That is the whole idea. A sharp corner is not the enemy of round circles, it is what infinitely many circles, each fixing one frequency, quietly agree on. Any repeating shape can be built from spinning arrows, and the shape itself tells you everyone